Hello guys, it's a pleasure being here. It's always a pleasure talking about the stuff that you like to work on. So that's exactly what I'm gonna present to you today. So I work at a company that we do online advertising. Okay, so basically we do personalized advertising. We're trying to see what you already bought, what you like, what you browsed, and we try to come up with the products that you're probably going to buy, and we do advertising to you. So the thing about Criteo is that we operate in 32 countries, basically around the world. We are partners to all the major e-commerces in most of the countries except China. And basically we have about 3 billion users. We have so many because they're actually in separate devices, and it's separate basically research topic, how to unite those devices, how to identify the same user. Basically there is a lot of users, a lot of user information. And also, since we have so many clients, about 30,000 companies work with us, collaborate with us. So basically even for this is actually numbers for Europe. It's just Europe, so we have 3 billion users, slash cookies, devices, and we have about 1 billion different products that we want to recommend to them. So you might imagine that this problem becomes very hard if you want to pick up which of products to who you want to recommend. And we often, to many things that we do, we want to know some stuff about it. So which products are similar in buyer's sense? I'm not going to define it properly here, but is a refrigerator more similar to a washing machine or more similar to a shower? Which of them are more similar to you as buyers? Probably you can realize that a washing machine is closer to a refrigerator or something. And we want to find which users have similar history. For example, they bought products that are similar. And the most important part, which products do we recommend to the guy, for example, that never went to eBay but went to other websites? How do we choose those products from eBay if they've never been mapped explicitly to the same thing? How do we do that? So there are multiple approaches to that, and one of the standard way to do that is the skipgram over the products timelines, basically prod to vec. It's known. So to get better perspective, how does it work? So for example, we have user timelines with some products in there, like PS4 and a washing machine and a bed. I don't know what for, but anyway. And then basically you treat those products as words, and you employ a skipgram model on that. So just to remind you, a skipgram model is a single layer neural network, basically, when you have two matrices of embeddings for every word or product in our case. And basically you take the dot product and you put it in through the sigmoid, and this is your prediction for the next product or the closest product. So what's wrong with it, right? Because everybody, a lot of companies use that. What's wrong there? The problem there is that you have a bunch of parameters. Basically, you have, for our case, you have about 400 gigabytes of data if you want to store it. Yeah, and basically you cannot train it on a single machine. And if you want to parallelize that, there are multiple ways to parallelize even shallow, models, basically. But the problem is if you want to store the whole, basically you have multiple nodes and you split your data. You do data parallel, for example, right? But then you have to distribute your model at every node so that it would be able to compute the gradients and send them back and somehow sync between them. But then you come back to the initial problem that you came from. You have 400 gigs at every node, which you cannot afford. And you have all the commodity node cluster, for example. Then there is an approach with the parameter server. Basically, all your parameters are stored in the parameter servers in a sharded way, basically the green thing here. And then you do shards of data. For example, take, you read your data, you request the needed parameters from the parameter server, you compute the inner product, you compute the prediction, and then you send over the gradient back to the parameter server, and parameter server in a synchronous fashion updates them. That's how most of the deep learning models are learned in a synchronous fashion, for example. But the problem with that is basically you will be setting a lot of communication, basically petabytes of data, because you have so much data, and you need to compute all these dot products and then send the gradients, and you need to do multiple passes. So basically it will be not only petabytes of data through the network, but it's very small packaging and basically billions of those small packages. So that is indeed a problem for an infrastructure point of view. Basically from technical point of view, you cannot train a word vec without occupying a very large cluster for a very long amount. So basically, it's super expensive to do that. You can do that, super expensive. And of course, there are ways to train word-vec skipgram models in a more efficient network avoiding communication way. But the problem is they require custom distribution schemes. Basically, you cannot do that on Spark. You cannot do that on MapReduce. You cannot fit in them. Basically, you need to build your own distributed infrastructure, your framework, a new framework, for example, what Yahoo did, which is also super expensive because it's software engineers working 6 months writing this new framework that you need for one specific purpose. So we were looking for something that would qualify for these three things. So it could be expressed in MapReduce and Spark API. Second, it will basically fit on the commodity servers, so that the memory requirements would be independent of the size of your problem, of your vocabulary. And then third, it would be nice if you could have the deterministic results, the thing that you never get with any non-convex optimization, even if you fix the seeds, but you train in a synchronous fashion, and network round trips are non-deterministic, so in the end you never get the same result. Which is actually a problem from an engineering perspective, because you want to be deterministic. Then it means you can do non-regression, you can control the quality of your, basically so that you don't break anything, or if you break, you see that right away. That's a very nice property to do. So what can we do? Basically, we were looking for an algorithmic solution. Basically, there's been some papers in 2015 that prove that skipgram is actually word-vec, is optimizing. What actually solving for is factorization of the sparse matrix with the entries where entries are PMI, pointwise mutual information of two products. And basically, they've shown that SVD over such a PMI matrix can have a compatible performance in terms of word-to-word similarity. And we thought maybe that's a great idea to do that, which might not seem at first if you don't know how to do SVD in a really distributed fashion on very large matrices. And basically that's what I'm going to tell you about. The first thing will be algorithmically, and a bit mathematically, not in a super rigorous fashion, but yeah. How does it work? The super scalable SVD, I don't know, what they teach usually at schools, for example, SVD for dense matrices is n cubed if you're looking for all the factors, but we're looking only for a subset of factors. So it's going to be kn squared, right? Still super large. If you work with sparse matrices, there are ways to do that, but still they require hundreds of multiplication by the same matrix. That is basically impossible if you're working with billions of rows and columns. But is there a way? So basically, yes, indeed there is a way. It was a long tail of research which was accumulated in a great survey in 2008, I think, or 2009. Basically, it sits on a very simple idea. So imagine you have a regular SVD with low rank SVD approximation. Basically you have some k factors there, I don't know, 10, whatever you want. And basically it is well known that it optimizes for the spectral norm of your approximation. So basically the key idea is if you have such a matrix Q, which has orthonormal columns, and these orthonormal columns are mostly can be represented as a linear combination of your main singular vectors. Then basically, and this Q is tall and skinny. Basically, it has few columns and the same number of rows. So if you happen to obtain such a matrix, then this problem, the SVD, reduces to some very simple and small computations. So let's just say we have this Q for a moment, okay? I'll show you later how to obtain it, but basically let's say we have it. We still don't know how to solve it, right? So the idea is, basically if we have this Q, Then we can decompose the Q transpose A. That's imaginary SVD, for example. And then we'll have this U hat, for example, right? And this U hat will be a matrix of size K times K, where K is the number of parameters that you're looking for. And then if you have this U hat, you can reconstruct the original U by just multiplying by a large matrix Q that you already had before. So how do we obtain this Q hat? Q hat is actually very simple. If you just multiply A by Q transpose, and you transpose that, and you do QR decomposition of this guy, and R is a K by K matrix, and then you decompose it, which is super simple. K by K is, if you're looking for 100 vectors, it's going to be 100 by 100, and it's going to be whatever. It's going to be upper triangular, but that's not super important here. So if we decompose it, then we actually effectively found our U hat. For free, so almost for free, because you just need to multiply some matrices, then you do QR, which is relatively cheap, and you do SVD on a very small matrix. And then you can find the original huge matrix of factors, essentially for free, if you can do multiplication at scale, of course. So then, the question is, how do we find this Q? How do we find this magical subspace, which is orthogonal to most of your eigenvectors, but not to the main one? So it's actually very simple. The approach is you generate a random matrix, which means just a matrix with random elements that you draw from some random distribution, like normal, uniform, whatever. It's not super important. The only thing important is that the columns will be linearly independent, which you almost guarantee if you generate them randomly. And it should have the same rank as you're looking for, a bit larger. And then basically you do power iterations. You just multiply G, the random matrix that we generated, by A and A transpose a couple of times. Not so many, maybe about 5 times, and you get very good approximation of the Q you're looking for. And then basically once you found the Q, you can solve the rest. How it is, just multiply and then do SVD on a small matrix. So, in theory, it looks like it's very simple if you can multiply large matrices, which is very parallelizable task and easy to distribute, easy-ish, at least it seemed. Then you can solve the problem, no problem. And the cool thing, this kind of approach has very good mathematical bounds in terms of error. Basically, when I found out this paper, it was 2013, I was super excited because basically, imagine you do honest SVD on your matrix A, and your rank that you're looking for, like 5 or something, I don't know, 6, whatever. The best approximation, basically the largest spectral norm of your of A minus your approximation will be basically sigma k plus 1, because basically that will be the largest singular value of the rest. This is the best you can get. But actually, if you apply this randomized method that I just described to you, and your matrix is like in billions, for example, the number of factors that you're looking for is k, 100. You do oversampling, so you do 100 plus 30, and you do only 3 power iterations, so which requires basically 7 multiplication by matrix. So you have a theoretical guarantee that your approximation will be just 4 times the sigma, which is great because usually the singular values of matrices decrease very quickly. So basically, if you do randomized thing with I don't know, like 100 vectors, it will be as good as 95 by the honest one, the full one. So basically, we have something that is independent of size and it does not require a lot of memory, because basically multiplication is very easy theoretically to do, because you partition your matrix in small blocks, so you distribute them, then you multiply, then you sum them up, and you're good to go. And the SVD is on the matrix of size k by k, so it's super simple. And you get deterministic results, because if you, the only non-deterministic comes from the matrix that you generate, but that's easy to fix with some seed. Now, how do we actually implement that? And the thing is, maybe in terms of mathematics, the multiplication part is the simplest one, but actually it's the hardest in terms of implementation, especially in things like Spark. So we just need four methods to implement in our MapReduce or Spark thing. And I'll start with the simplest one, basically how do we generate a random matrix. So first of all, let's go how we, what kind of data structures we use to represent our large sparse matrix A. So basically it has, we split it in blocks and then we partition those blocks together in terms of sparse. Then how do we generate a random one? So we generate enough empty partitions with some seeds, and directly on every node we generate the random blocks in there. It's super simple. Then second method that we need is tall and skinny multiplication by a single block, the one that we need to restore the original U, the factors that we're looking for. So it's actually very simple in Spark. The C is of size 100 by 100, so you can send it all over the network to all your nodes and basically use broadcast in Spark and then multiply locally and then persist, and you have it. It's very simple, almost trivial. Then with the QR decomposition is a bit harder, but still very easy to do. So basically, you have your tall and skinny matrix that is split in basically it has one block per partition in terms of width, and you do QR at every partition level. So you squish them together and you do QR, and you send your R further, and basically you do tree reuse. And at the end, you're guaranteed to have the same R as if you did QR on the full B. Basically, there is a paper by Konstantin 2013, which proves that result, and it's very neat. And actually, at the end, when you have this R, how do you find the original Q, which you're looking for? Is just you multiply B by the small block that you invert. And since it's 100 by 100 and it's upper triangular, it's almost trivial to invert. It's very fast, very simple, and uses the method that we just defined before. Then the hardest part in terms of implementation is, of course, the conceptually simplest part is actually multiplication. So basically, how do we do that? Let's imagine we're implementing it right now. So we have a huge sparse matrix separated into sparse blocks and partition, and we have our B. So how do we do that? How do we multiply? So the first is, let's do shuffle partition. So basically we send the blocks, whatever blocks of B are needed in this partition, we just ship them there, and it's going to be fine. And actually a very workable thing until your matrix increases in size. Because if you think about it, the B is in size of n times k, and you send it as many times, as many row partitions you have in A. You need to duplicate it, basically, and write it in shuffle. And the thing is, when your B is 400 gigs, and your A is also very large because it's n by n, it has like 1 billion times 1 billion, then basically the shuffle size is basically n squared and grows very large, very quickly. Basically, you have 40, 100, 200 terabytes of data to shuffle, which is very large, very heavy on the cluster. So as the size grows, you need to find another way. Let's be clever and do something in Spark that will allow us to do that. For example, we split A by columns in terms of partitions, and then ship only every block only once to every partition. So that's easy. Shuffle, basically almost no shuffle. You do zip partitions with that, and then it computes the output. The problem there, Spark has to store all the result of your computations in memory. So basically, you need, if you do that, if you multiply B1 by the sparse row of A, you will end up with the matrix of size B, initial one, in a single node, which is what we wanted to avoid. So we cannot do that. So can we do something in between that still fits in memory? Yes, we can. So basically, it's achieved we achieved that by splitting A into multiple RDDs, abstraction in Spark that we use. So basically, if you split A by row blocks and then partition them by columns, do zip partitioning, and your B will be in memory most of the time. Then you sort of limit the constants on how you shuffle but basically here, if it's just stored in memory, then B won't cause any shuffle. And we can basically do that. So we still get some overhead from the splitting A into multiple RDDs, but that can be implemented in a very efficient way as well. So basically, now we express this algorithm in terms of MapReduce and basically Spark API. Basically, we do that for Criteo for matrices usually of 100 million or something like that. Basically, we open source the implementation. It's on the GitHub, Criteo GitHub. You can search it. It's called Spark RSVD. You can fork, use it, whatever. Yeah, and of course we accept any PRs, whatever issues you create. So, any questions?